Hello everyone, welcome back to my channel. My name is M. Ganeshmani, USN1B 22EC056, pursuing my BE at Shri Venkateswara College of Engineering in ECE stream. The course name for today's video is Digital Signal Processing and the course code is BEC502. So by looking into this image, we can understand that this is a signal. So we'll be understanding the classification of signal in today's video. The contents that we'll be covering in today's video would be a lot about the signals, their classification, their properties, and how many classifications are available. So we'll be looking into the definition and types and classification of signals. So first we have the definition. In digital signal processing, DSP, a signal is a function that conveys information about the behavior or attributes of a physical system. It represents a physical quantity that varies over a time, space, or any other independent variable. Signals are typically used to model, analyze, and process the data in various domains, such as audio, video, communication, and control system. So now we'll be looking into the key points. So first it is mathematical representation. Signals are expressed as functions. So continuous time signals such as x of t, x varying with respect to time t, and discrete signal is x varying with respect to n. N is the instant of time. At that time only the signal will vary, not all the time. Whereas continuous time signal will be varying with respect to time. So purpose. Signal carry information that can be analyzed or manipulated for specific application. Types. Signal can be classified into categories like analog, digital, periodic, aperiodic, deterministic, random, energy and power. For example, a sound wave captured by a microphone is a signal that can be processed by removing noise and enhancing the quality to extract specific features. Continuous and discrete time signal. The definition of continuous time signal is that the signal that are defined at every instant of time, that it does not vary with respect to time, is known as continuous time signal. The representation is shown as follows, expressed as x of t, where with respect to t the x value varies at all the instant of time. Characteristics can be taken any value at any time, often used in analog system like voltage, temperature, etc. Example, sine wave x of t is equal to 2 sine of 2 pi ft, x of t is equals to sine of 2 by pi ft. These are the examples, and in real time it is heartbeat ECG. Discrete time signal. Definition of signal defined only in a discrete interval of time is known as discrete time signal. Like at the particular instant of 1, 2 or 0.1 the signal is observed, rather than apart from that 1, even if it is 0.001 also is increased or deviated, that said it can't be observed. So that is where discrete time signal comes into the role. Representation is x to the x in place of n, where the n is the instant where the signal is occurring. Characteristic defined only for specific point of time, common in digital system, and sampling continuous. Example, audio sampled at regular interval, digital images represented in pixel grids. Next up is the analog and digital signal. Analog signals definition. Continuous signals that represent the physical quantities with infinite possible values. Characteristics. Amplitude can be taken any value in any continuous range, no limited to specific level. Susceptible to noise and distortion during transmission. Application. Audio temperature reading. Example, a sine wave representing sound pressure over time. Digital signals. Definition. Discrete signals that represent data using binary values like zeros and ones. Characteristics. Amplitude is restricted to specific discrete level. Robust against noise due to quantization. Easy to store, process and transmit using digital. Application. Digital audio video. A sampled version of an analog signal converted into binary form is an example for the digital signal. So next we have periodic and aperiodic signal, where we can observe the continuous time signal x of t is said to be periodic with period t if there is no positive non-zero value t, for which x of t plus t is equals to x of t for all 1 is to t. An example of the signal is shown in figure 115.8, that is we can see on the left side, that is there is a triangle where with respect to t there is only digitally periodically it is increasing, and aperiodic we can see that it is not uniform in the same value, it is one higher, one lower, one higher, one lower, one higher, one lower. So that is where it is, where you have uniform amplitude rise, that is periodic. Where you don't have any kind of uniform amplitude rise, that is aperiodic. So further we can analyze the equations that x of t plus m of t is x of t, and further we have f naught is equals to 1 by t naught of hertz, where fundamental time period t naught will gives us the frequency, and omega gives us the angular frequency by 2 pi of f, which is 2 pi by t. So there, with this, we can come out with the equation that is x of n plus m of n is equal to x of n. So by this, we can understand that periodic means there is a similar amplitude rise, whereas in aperiodic means there are two amplitude rises that operates periodically, like one higher, one lower, one higher, one lower. So this is where aperiodic and periodic comes into role. Next, we have even and odd signal. In even and odd signal, a signal x of t or x of n is referred to be even if x of minus t is equals to t, it is continuous, x of minus n is equals to n, it is discrete. But when x of minus t gives us the positive term, or any of the x of t or x of n gives us a positive output, it is said to be even. When t is less than 0, the mirror image is up-plane. When t is greater than 0, we can object the function, and the function signal x of t is cos of omega t, even because of cos of omega t is equal to cos of minus omega t. And for odd function, we can observe that when x of t or x of n, the t is repeated in a negative value and we get a negative output, it is said to be as odd function. Here we can observe the odd and even function signals at a and b, that is there is a rise with same level with both minus t and plus t, there is no difference. But whereas in down we can observe in c and d, that is there is a difference, like in minus it is minus, in plus it is plus. For even always it is positively occurred, but in odd, when there is positive, that time only we can observe positive. When there is negative, there we can observe negative. So that is where we can discrete it is odd or even signals. Now, energy and power signals. Consider a resistance R, excited voltage V, and producing a current. Let us assume that R is equals to T. We have x of t, V of t is equals to x of t, P of t is equals to x square of watt. So here we can understand that I of t is equals to V of t and x of t, where I of t is the current, V of t is the voltage, and x of t is the value provided. So here we are analyzing the signals with respect to the energy and power. For energy, voltage and current is required. So the instantaneous power expanded R is equals to 1, which is given in resistance is equals to 1 ohm. Next, we have P of t is equals to x square of t watts. The power design in 1 ohm is normalized the power, the total energy, average power. P of the signal x of t R is equals to integration minus infinity to plus infinity x square of t. And P is further given the limit with respect to 1 by t, that's the frequency, 1 by time period, from minus t by 2 to plus t by 2 x square of tt. In order to remove the infinity, we are applying the limit. And then we have further modularized the equation, like my e is equals to minus infinity to plus infinity modulus of x of t of whole square. And to remove that also, the limit from minus t to plus t by 2, we are applying the limit. And further, by applying the limit, we get the equation p is equals to 1 by t 0 to t x square of t from x of t. Then e is equals to signum function of a minus infinity to plus infinity x of n square. The limit of n varies till infinity, 1 by 2 pi n plus 1 signum function of the given value n from minus n to n. So x of n square. So the total average equation, by solving this, we can understand that 1 by n is equals to n of 0 to n minus 1, signum function of n of 0 to n minus 1 modulus of x of n whole square. So this is where we can obtain the equation for energy and power signals. So in this video, we understood about the classification of signals. So at last, I want to conclude by saying that classifying signals is in digital signal processing essential for understanding their behavior and choosing appropriate process techniques. Signals are categorized based on time, continuous or discrete, amplitude, analog or digital, predictability, deterministic or random, and other properties like periodicity and symmetry. And each type of signal serves unique application in fields such as communication, audio, and processing and control system. By identifying the signal characteristics, engineers can design efficient systems to analyze, manipulate, and transmit information. The foundational knowledge is crucial for advancing the technology and optimizing real-world signals and applications. Signals classification are constant for every DSP aspirants, and for any of the engineers ahead for the future studies also, everywhere this comes into role. We need to understand how the signals are classified in order to have a clarity. As for telecommunication engineers, electronic communication engineers, as we electrical engineers, this plays a vital role for us, and we need to understand this property properly. Thanks for watching this video. Please do like, share and subscribe to my channel. Hit the bell icon for further notifications. Stay tuned for more upcoming videos. Goodbye.